Hi everyone, I'm Sleepless Scientist, and tonight we're lying here together in the stillness, our minds wandering beyond the walls, beyond the trees, and way beyond the reach of your phone signal. Somewhere up there above all the noise are the stars, cold, bright, silent, and you're wondering, why do they twinkle so calmly when light is moving at such a ridiculous speed, or more precisely, why can't light go even faster? What's it running from? Who decided that 299,792,458 meters per second was enough? It's such a specific number for something so universal. Light zips through space at this exact speed, like it's trying to beat traffic and it never breaks the limit. But if the universe isn't policed by cosmic speed cameras then, why the restraint? Before we dive too far down the wormhole, let me ask you this. I'd love to know where in the world you're listening from and what time it is for you. Let me know in the comments below. I'm always curious where these quiet little science stories are drifting to, and if this video helped you while you were there. Now relax, take a deep breath, and join me gently on this evening's journey. You shuffle toward the window. Maybe it's midnight. Maybe it's 4:30 a.m. Either way, you're staring at a darkness that stretches so far, your thoughts start to dissolve into it. You squint at a little point of light. A star. Maybe a planet. Maybe it's just a reflection from the street lamp. But whatever it is, it feels distant. And tonight, that distance whispers something new. Why does light take time at all? Because it does. Even light, the champion of speed, takes time to move from place to place. From the sun to your face. 8 minutes. From Alpha Centauri to Earth over 4 years. From a galaxy at the edge of the observable universe. That's 13.8 billion years. Minimum. This means when you look into space, you're looking backward in time. The light reaching you now left those stars before you were born, before the pyramids were built, before there were even eyeballs around to see it. Which weirdly enough makes your bedroom window a kind of time machine. If light had no speed limit, if it were instantaneous, then the whole universe would be visible all at once. Past, present, future, all layered on top of each other like a very confusing lasagna. But it isn't. Because light, fast as it is, has a very clear top speed. It doesn't speed up if it's in a hurry. It doesn't slow down unless you force it to. And this speed, this incredibly fast but not infinite speed, is how the universe keeps order. Here's a wild side fact to warm your skeptical heart. Sloths can hold their breath longer than dolphins can. Seriously. Dolphins breathe consciously. They need to surface regularly or they risk drowning. Sloths, on the other hand, can slow their heart rate and just chill underwater for up to 40 minutes. It's nature's passive-aggressive power move. You lean on the windowsill, now your arm's a little cold. Outside, a car passes its headlights, slicing through the air. The beams don't feel slow right, but they're not instantaneous. They move. They traverse. They cross. The only reason it seems so quick is because your brain is lazy. It edits reality like a tired film student on deadline. You think back to elementary school, remember the time your teacher told you that light is both a particle and a wave. You blinked. You nodded. You definitely didn't understand. And yet here you are all these years later, replaying that strange phrase, the speed of light. It rolls off the tongue like a law of nature, but it's really a boundary, a border, a you shall not pass moment coded into space-time itself. What's so special about that number? Why that speed and not 10 times faster? Scientists still debate whether the speed of light is truly a property of light itself, or if it's just a reflection of how space-time behaves when we try to measure anything moving at all. Some physicists suggest that light is simply showing us the rules that space and time already agreed upon, like an overachieving intern following protocol. You step back from the window and flop back onto the bed. The blanket rustles. Your foot hits something, probably that book you were pretending to read earlier. Outside, the stars keep glowing. Not because they're glowing now necessarily, but because they were glowing a very long time ago and the news is just now reaching you. And it will always be that way. Light will always take time. Stars will always appear younger than they are. And you will always be a few minutes or millions of years behind the truth. It's strangely comforting, though. That delay means we live inside a story that's unfolding piece by piece, light second by light second. So you sigh. You adjust the pillow. You squint again at that star in the sky. It's still shining, even if it died before your great-great-grandmother was born. And somehow that delayed flicker feels like a lullaby. You reach out towards the windowsill again, fingers grazing the cold glass like, maybe if you could just push your hand a little farther, you could touch the light. But of course you can't. Because even though it feels like that star is right there twinkling just for you, the truth is it might not even exist anymore. It could be gone, exploded, faded, collapsed into some cosmic retirement plan of a black hole. But you wouldn't know, because that little beam of light is still playing catch-up, traveling millions or billions of kilometers just to make its fashionably late entrance into your sleepy eyeballs. And here's the curious bit. This isn't some philosophical delay. It's physics. Pure, stubborn rulebook physics. Because light doesn't cheat. It moves exactly as fast as the universe allows, no more, no less. Even when it's been traveling for thousands of years across empty space, light never picks up speed. It never burns out. It just keeps going. Like a cosmic mail carrier with no lunch breaks. You think about this for a second. That little photon left its star before human civilization figured out plumbing. It's been alone in the dark, sprinting silently through space, avoiding dust, dodging planets, slipping past black holes, all to land right here, right now, on your retinas. No wonder it's tired. And here's the wild twist: even though light seems to be everywhere, flooding out of bulbs and phones and sunrises, it's actually kind of delicate. One well-placed atom and poof, it's scattered, lost, absorbed. That's why the night sky is mostly black. Because light may be fast, but it's also a bit of a diva. It needs a clear runway, otherwise it gets distracted or worse, canceled. Which is why starlight feels so sacred. It's not just arriving, it's surviving. You lie back down, still chewing on that. Imagine every time you see a star, you're seeing a fossil made of photons, an echo, a whisper from deep time. It's not a live broadcast, it's a memory. And oddly, that makes the darkness feel less empty, like the sky is filled with letters from the past. Some scientists even think that if we look far enough, we might see the beginning of time itself. The cosmic microwave background, a dim glow left over from the Big Bang, is still floating out there 13.8 billion years later, like the universe's baby photo. A blurry, pixelated, slightly embarrassing snapshot of our earliest days. It's faint, cold, fuzzy, and still moving always at that same relentless pace. 458 meters per second. You blink at the number again. It's so precise it feels artificial, like someone measured it with a really good stopwatch and said, "Okay, that's it. That's the speed TM." But it's not artificial, it's fundamental. The speed of light is baked into the very fabric of space and time. It's not just how fast light moves, it's how fast causality moves. It's the speed of everything that can possibly matter. And yet, light still takes its sweet time. the moon 1¼ seconds away, the sun. 8 minutes, Pluto. About 5½ hours. Proxima Centauri, our closest stellar neighbor, more than 4 years. So every photo from space, every telescope image, all of it is history. Gorgeous, glittering, very well-lit history. Meanwhile, here on Earth, light still acts like it's the hottest thing in the room. And to be fair, it kind of is. Did you know that some deep-sea creatures have bioluminescent butts? Not just for show, they use it for camouflage. The glow mimics faint sunlight from above, hiding them from predators below. Which is funny, because light down there is more of a rumor than a reality. You think of those creatures now, floating in inky blackness, flashing their little lights like living disco balls, unaware they're part of the same game as the stars above you. Because whether it's a cosmic ray or a fish butt light plays by the same rules. And those rules are weird. See, for a long time, scientists weren't sure if light was even real. Like, obviously you can see things, but is light a thing, or is it just a behavior? Newton thought it was particles. Huygens thought it was waves. Then some brilliant 19th century physicists said, why not both? That's way more confusing. So now we live in this delightful paradox where light is a wave-particle hybrid with commitment issues. Sometimes it acts like a stream of bullets. Other times it behaves like ripples in a pond. And it always travels at the same speed through a vacuum at least. Even when you chase it. Even when you run from it. It doesn't care. Einstein noticed that. He said, if the speed of light is always the same no matter what, then time and space themselves must stretch and squeeze to make that work. That was the beginning of relativity, one of the biggest what moments in science history. Scientists still debate what light is at its core. Is it a vibration in the electromagnetic field? A probability wave? A tiny dancing string from a hidden dimension? Nobody knows for sure. But we do know this light has a schedule, and it's never late. You roll back toward the center of your bed, letting that last thought settle. Outside your window, the stars keep whispering their ancient secrets. And now you know they're not whispering to you. They're whispering to anyone who happens to be listening billions of years after the fact. Tonight, that someone just happens to be you. You're still lying in bed, the stars fading slightly behind a curtain of sleepiness, when a peculiar image sneaks into your brain, Einstein. But not the chalkboard version. Not the wild-haired black and white Nobel Prize-holding portrait you've seen 1,000 times. Nope. This one's barefoot in pajamas padding around a creaky apartment with a mug of lukewarm tea. His hair still wild, sure, but this is the Einstein before the world cared what he thought. The insomniac Einstein. The thinking too much to sleep Einstein. You'd get along. It's the late 1800s, and our pajama-clad philosopher is obsessed with a thought experiment. What would it be like to ride a beam of light, like if you could somehow grab hold of it and surf along beside it? What would the world look like? That simple, absurd, beautifully childlike idea would eventually shatter everything we thought we knew about time, motion, and reality. You imagine him pacing around his apartment, muttering things in German, forgetting where he left his tea, and whispering, Warum ist das Licht immer gleich schnell? Why is light always the same speed? Because that's what made Einstein different. Everyone else assumed light's speed must be relative like cars on a highway. But Einstein, he said, nope. Light doesn't care how fast you're moving. It just does its thing. And if that's true, then the whole concept of time has to bend. Because otherwise, things don't add up. It's like trying to watch Netflix while your Wi-Fi keeps changing the rules of math. Reality would glitch. So Einstein made a decision. If the speed of light stays constant, then time itself must be flexible. which is wildly counterintuitive. Time feels so sturdy, so reliable, but no, turns out it's stretchy, malleable. You can twist it if you're moving fast enough. And that's when relativity stepped into the spotlight. Here's how it goes. If you're moving at a significant fraction of light speed, time slows down for you compared to someone standing still. It's not an illusion. It's not a trick of perspective. It's physics, proven. Clocks tick more slowly. Heartbeats drag. Entire lives stretch out like soft caramel. This phenomenon is called time dilation, and it's real. We've measured it with astronauts. Their wristwatches run just a little slower than ours. So yes, technically, astronauts age slower, which might be why they always look so cool and ageless in interviews. Even GPS satellites have to correct for this. They're flying so fast and so far above Earth's gravity that their internal clocks run just a bit differently than ours. If we didn't correct for relativity, your phone would be wildly wrong about where your favorite noodle shop is. So thank Einstein for your lunch plans. Now, quick palate cleanser. Did you know wombat poop is cube-shaped? Yeah, tiny weird brown cubes. Nobody fully understands why. It has something to do with their slow digestion and the unique elasticity of their intestines. Nature's bizarre version of dice. Anyway, back to Einstein in pajamas. One night, after years of scribbling formulas on napkins and doubting himself so hard it hurt, he wrote the most famous equation in human history, E equals mc2, which basically says energy and mass are the same thing, just in different outfits. And because light moves so fast, even tiny bits of mass can hold enormous energy. It's like discovering your backpack weighs a kilogram, but can explode with the force of 1,000 suns. Hopefully, you're not packing uranium. But that equation isn't just about bombs or physics papers. It's the doorway to understanding why light matters. Because light doesn't just illuminate, it defines. It gives shape to time boundaries, to causality, and rhythm to the entire universe. And Einstein. He didn't just ride a beam of light in his imagination. He broke it open and showed us what was inside. Of course, scientists still debate whether Einstein's version of reality is the final word. Some argue that deeper, more chaotic layers of physics exist beneath relativity, where quantum weirdness reigns supreme. But one thing's certain, Einstein gave us a map, a way to navigate a cosmos that behaves less like a machine and more like a dream. You close your eyes now, not because you're asleep, but because your brain is full. You picture that young Einstein again, scribbling equations by candlelight, not to impress anyone, not to change the world, just because he had to know. And here you are, a century later, still wondering about the same beam of light, still imagining what it would be like to catch up with it, still listening for the echo of his quiet thought experiment drifting down through space-time like a lullaby in German. Your blanket's bunched awkwardly around your feet now, but you don't fix it. You're busy thinking about that beam of light, the one Einstein tried to ride, the one that defines how everything moves and stretches and behaves. It's strange, isn't it? That light of all things has a maximum speed, not the fastest car or rocket or internet service provider. Light. The quiet, obedient child of the universe. But the real kicker is this: nothing, not even the wildest particle, can go faster. And the reason isn't just about light. It's about the structure of reality. The speed of light is more than just a measurement. It's a cosmic speed limit built into the geometry of space and time. If you were to draw a diagram of everything that could possibly happen to you from this moment forward, it would look like a cone spreading upward through time. Everything inside that cone is reachable. Everything outside of it, impossible. out of bounds. That's because light defines that boundary. If something lies beyond what light could reach, then you can't reach it either. And no matter how hard you push, no matter how much energy you throw at the problem, you will never break that boundary. Why? Because as you speed up, you get heavier. Not just in the holiday dessert way, but in actual mass. Physics punishes your ambition by making you more difficult to move. You could pump more and more energy into yourself approaching light speed. But as you get closer, your mass would skyrocket, approaching infinity. And since it would take infinite energy to move something with infinite mass, well, good luck with that. The universe is in its own strange way, passive-aggressively protective. You're not allowed to go faster because it would break the math. Rip open causality. Let effect happen before cause. Cats walking dogs. Coffee unstirring itself. Basically full chaos. Scientists still debate whether anything at all could cheat this limit. Maybe in some bizarre twist of space-time, a wormhole, a shortcut, a warp bubble, you could appear to outrun light. But you wouldn't actually go faster. You'd just trick the map. Like folding a piece of paper until two dots touch. But in regular old space, the laws are firm. No one outruns the photon, which kind of makes light. Royal, the monarch of motion, the referee of reality, the world's most energetic diva with a crown of physics equations. And yet some things get so close. Cosmic rays, high-energy particles flung from supernovae. They blaze through space just a hair under the speed of light. We've measured them. They're absurdly fast. But even they stop just short of the finish line. It's as if the universe put a velvet rope across the last nanometer per second and said, sorry, VIPs only. Meanwhile, here's a fun thought. Bananas are radioactive. Not dangerously so, don't throw yours away. But they contain potassium-40, a naturally occurring isotope that emits tiny amounts of radiation. Eat enough bananas and you could technically set off a sensitive radiation detector. Although if you're eating thousands of bananas in one sitting, radiation probably isn't your biggest concern. Anyway, you lie there now, still eyes half closed, thinking about this universal limit. And it's not just a speed cap, it's a truth boundary. A wall that separates what's possible from what's not. A bright, invisible line that keeps the universe from spiraling into absurdity. Because without that limit, everything breaks. Time travel becomes trivial. Communication happens faster than thought. Paradoxes bloom like weeds, and cause and effect unravel. But with it, the cosmos behaves. Stars are born and burn and die on schedule. Planets orbit in predictable rhythms. Even your heartbeat plays by the rules, one beat at a time, no skipping ahead. So you start to see the limit, not as a restriction, but as a gift, a kind of galactic governance. Like the handrails on a mountain trail, you might grumble at them, but they're the reason you're not falling into an abyss. And the speed of light isn't just a number, it's the very scaffolding of reality. Without it, there is no now, no here, no you. Scientists still debate whether this limit could shift in extreme conditions, near black holes, inside high-dimensional brains, or during the early seconds of the universe. But here in your cozy human frame with your sleepy human brain, it's fixed, immutable, and that's oddly comforting. You nestle deeper into the bed, finally tugging the blanket over your toes. Your breathing slows. The ceiling stares back, dark and friendly. And somewhere out there, a photon continues its endless journey across the void. Unstoppable, unchanging, bound not by engines or friction or fuel, but by a law so pure it shapes everything you'll ever know. You sigh again, because somehow knowing that limit exists makes the universe feel less chaotic, less scary. It's not a cosmic prison. It's a frame, One that lets the story of everything unfold page by page at a pace we can understand. Light speed, just fast enough to be magical, and just slow enough to make you wonder. You dream you're running. Not the kind of running where you're late for a bus or forgot your shoes. This is cosmic running. You're gliding through empty space, chasing a beam of light. It looks like a silver ribbon forever just ahead of you, teasing, daring you to catch up. And you push harder, faster, past rocket speeds, past particle collider speeds, past every speed limit your body or physics has ever known. But no matter how close you get, it stays ahead, like it's moving away just fast enough to keep you behind. And then you wake up. Your heart's not racing. You're not sweating. Just floating there, blinking into the soft dark like, wait, why can't I ever catch it? And now you know. Because light's not just fast, it's the fastest. It's not even trying to outrun you. It just exists at the outer edge of possibility. So you start to imagine this chase for real. You a particle maybe, or a spaceship of the future, blasting off with engines so powerful they'd make Elon Musk blush. You pass the moon in seconds. The outer planets gone in a blur. The sun fades behind you. And yet, light still wins. Why? Because as you go faster, time starts to stretch. Space starts to bend. Your mass increases, dragging more and more inertia behind you, like a wet mattress strapped to your back. You can approach light speed. You can flirt with it. But you can never get there. Not unless you become massless, like light itself. And yet there's a loophole, a cosmic curiosity that makes physicists lean forward in their squeaky chairs. What if you could slow light down instead? Sounds crazy, right? But it's been done. In certain substances like dense glass, cold atomic gases, or even Bose-Einstein condensates, scientists have managed to slow light to a crawl. In one experiment, they got it down to 17 meters per second. That's slower than you on a lazy walk to the fridge. They even stopped it, briefly trapping photons like fireflies in a jar of quantum molasses. How? By manipulating the medium, basically playing with how atoms interact with light waves. The light isn't destroyed, just held. Paused. Like pressing pause on a cosmic remote control. Which is nuts, because if you can slow it, can you ever speed it up? Well, no, not in vacuum. That upper limit still stands tall. The cosmic speed cap only applies to light in empty space. But inside materials, the rules get fuzzy and fascinating. Scientists still debate whether slow light counts as light at all. Some argue it's more like information about light being passed along by excited atoms, like a game of telephone played with photons. And guess what? In water or glass, light already moves slower than in a vacuum. That's why pencils look bent in a cup of water. The light entering your eye is refracted, bent, and delayed because it's taking a scenic route. Which leads to a wonderful fact: you've seen slow light every time you've looked through a window. You just didn't know it. Here's another random gem while we're here: sharks are older than trees. Seriously, sharks have been around for about 400 million years. Trees, a mere 350 million. Which means somewhere a shark probably rolled its eyes at the first tree like, ugh, hipsters. Anyway, back to light's strange slowness. Even when slowed down in glass or fiber optic cables, the information in that light is still constrained. You still can't send a signal faster than light travels in a vacuum. Nature won't let you cheat. It's like light is the ultimate pacemaker. It sets the rhythm. Everything else dances to it. And you realize something strange now. The speed of light isn't just about light. It's about everything. If you somehow changed that speed, turned the cosmic dial up or down, it would rewrite reality. A faster light speed might make atoms unstable. A slower one could make stars impossible. Time might drip instead of tick. The whole structure of causality would melt. That number 299,792,458 meters per second isn't a random cosmic hiccup. It's a load-bearing wall in the architecture of the universe. And you're stuck inside it. But not trapped. Held. Which is kind of beautiful. You roll over, letting that thought swirl. Light, the thing you barely notice when flipping a switch, is secretly the scaffolding of existence. It rushes, stretches, slows, reflects, and defines what's real. And sometimes, under just the right conditions, it slows enough for you to see it for what it is, not just illumination, but structure. Not just speed, but law. Your eyes flutter open again, not because something startled you, but because your mind is chewing on something sticky. If light is the fastest thing in the universe, you think, then what exactly happens when you try to beat it? Not that you can. You've already made peace with that. But suppose you tried. Suppose you really went for it, cranked your engines, leaned into the cosmic wind, and tried to push past that unbreakable number. What happens? The answer is, everything breaks. First, there's mass. Remember how getting faster makes you heavier. That's not metaphor, it's math. The closer you get to light speed, the more energy it takes to keep accelerating. At 99% the speed of light, it takes an absurd amount of fuel. At 99.99999%, it's basically all fuel and no spaceship. Then there's time. It slows down for you as you accelerate. Which sounds cool, like becoming your own time traveler. But to an outside observer, you're basically frozen. In the thought experiment, where you reach light speed, time would stop altogether. You'd see the entire universe in a frozen snapshot. No movement, no ticking clocks. Everything standing still forever. And here's the kicker: for light itself, time doesn't exist at all. From a photon's perspective, there's no journey. No 8 minutes from sun to earth. No millions of years from distant stars. Just emission and arrival. The trip is instantaneous from its own frame of reference. Wrap your sleepy brain around that light doesn't experience time. You sit with that for a second. Light is eternal and immediate. It's always now. You, on the other hand, are a puddle of organs and calendars. Fair trade. Scientists still debate whether this means light actually experiences anything. After all, it's massless. It doesn't have memory or perspective. But the idea that something can move through space without time, that's a poetic level of strange. Now let's say, just for the sake of midnight mischief, you somehow pushed past the speed of light. You're in uncharted territory. Not just fast, too fast. Weird things start happening. For one, your mass becomes imaginary. Not unicorn imaginary, mathematically imaginary, as in the square root of -1. Your equations collapse into nonsense. You cease to be describable by the laws of physics as we know them. Causality shatters. Effects happen before causes. You could see a glass shatter before anyone throws the rock. Send a message to someone before you were born. Cancel your lunch order after eating it. And this right here is why the universe enforces its speed limit so ruthlessly. Because if you go faster than light, you can go backwards in time. And once time becomes a playground, nothing makes sense. You could murder your own grandfather. You could win the lottery by emailing your past self. You could accidentally delete the universe. The universe is dramatic like that, so it doesn't let you. Even particles accelerated in giant machines like the Large Hadron Collider never reach light speed. They get close, absurdly close. But the closer they get, the harder it is to push them any faster. It's like trying to run through syrup with anvils tied to your feet. Nature politely says, "That's far enough." But here's where it gets fun. What if there were particles that could go faster than light? Physicists have dreamed up something called tachyons. Hypothetical particles that always move faster than light. They'd never slow down below the speed of light. That would be like us trying to stand still at 0 mph. It's just not in their nature. But tachyons come with baggage, because they'd reverse causality. They could arrive before they were sent. They'd turn cause and effect into a suggestion. And well, no one's ever seen a tachyon. They might not exist, but they could in theory. And that in theory keeps theoretical physicists up at night and makes late-night YouTube scripts far more interesting. Here's something lighter to balance things out. Octopuses have 3 hearts. 2 pump blood to the gills, 1 to the rest of the body. And when they swim, the body-pumping heart takes a break. So technically, exercise stresses them out so much that they literally lose heart, which frankly is relatable. Back to your faster-than-light joyride. Even if you somehow skipped past all the physical constraints, you'd still face a bigger problem: information. Because information like mass and energy can't move faster than light. If it did, we could break encryption, predict quantum outcomes, and get spoilers for next week's episode of Life. And physics hates spoilers. So even when particles appear to communicate faster than light, like in quantum entanglement, no usable information is transmitted. Just correlations, ghostly echoes, a wink across the cosmos, but never a full message. The universe keeps its secrets until the timing is right. You breathe in slowly, realizing the absurd genius of this. The speed of light isn't just a rule for movement, it's the limit for knowing. Nothing is real to you until light tells you about it. Without that limit, reality would arrive all at once. No sequence, no suspense, just an overwhelming flood of everything everywhere forever. Instead, you get life at light speed, moment by moment, scene by scene, like a cosmic bedtime story, unfolding one page at a time. You're still drifting on that thought, tangled in imaginary tachyons and ghost particle paradoxes, when a new question sneaks in like a cat at the foot of your bed. If light's so fast, why can it slow down at all? You've seen it bent straws in water, rainbows in a puddle, sunlight splitting through a prism like a drama queen at prom. Every time light enters something thicker than air, glass, water, even diamonds, it slows down, changes direction, gets bent. Not because it's shy, but because it has to follow the rules of the medium. You picture it like this. Light is the universe's fastest runner. But sometimes it walks into a party, say a piece of glass where everyone's standing, shoulder to shoulder, awkward and jiggling with atomic energy. And light, ever polite, slows down. It bumps into the crowd. It waits. It zigzags, it stumbles. Not because it's tired, because it's interacting. This is called refraction, and it's what makes lenses work. Glasses correct your vision, and rainbows exist at all. But the light itself, between those little stumbles, it's still moving at full speed. It's just constantly being delayed. Imagine running across a dance floor full of clumsy toddlers holding balloons. You're still fast, but there's a lot of dodging involved. And here's where things get especially weird. In certain experiments, physicists have slowed light down to a few meters per second. Some have even stopped it, trapping it in a cloud of atoms like a bug in amber, only with more lasers and lab coats. So is that really light? Well, scientists still debate this. Some argue it's not the light itself that's standing still, it's the information about the light, like passing a message along a line of whispering atoms. Others say, nope, it's the real thing, paused but preserved. Either way, it messes with your intuition. You'd think light should always be light speedy, but it turns out it's a little more adaptable than that. More like an introvert at a party, fast when alone, slower in a crowd. Here's a fun twist. Cherenkov radiation is what happens when a particle actually does move faster than light, but only in a medium like water. Wait, what? Yes. The key is that while nothing can go faster than light in a vacuum, light in a medium slows down. And if a particle barrels through that medium faster than light does, it emits a glowing shockwave like a sonic boom, but visual. This eerie blue light glows in nuclear reactors in deep water, even in the cooling pools of spent fuel rods. It's like the universe's way of saying, whoa there, particle. You're breaking the local rules. Lights on. And it's beautiful, even a little spooky. You've seen it in movies without realizing those glowing blue reactor cores humming softly with impossible light. And now you know. It's the afterimage of speed. Now, while we're swimming in the strange bananas glow under UV light. They do. Ripe bananas emit a blue fluorescence invisible to the human eye. Scientists think it has something to do with chlorophyll breakdown. Either way, bananas are just out here being sneaky bioluminescent snacks. Back to our beam. You start to see light not as a speed demon, but as a communicator. A translator between space and time. Between this happened, and you now know about it. It's how you see the world, but also how the world becomes real to you. Because light is information. And all information, every photon bouncing off a tree or a person's face or the microwave burrito you probably forgot, takes time. Even now, as your eyes adjust to the dim glow of your bedroom, the photons bouncing off your ceiling are taking nanoseconds to reach you. Not much, but enough. Enough for you to feel the delay, the softness, the reality that even the present is made of slightly outdated news. And that's kind of wonderful, because that delay, that gentle lag, is what makes dreams possible. You're never trapped in now. You're floating in it one light second at a time. So when you look at a star and it twinkles just so, know this, you're not seeing a star. You're seeing history. A ghost of brightness that left its home long before your feet ever touched Earth. And that's the world we live in. A world where light shows up late to every party, but still brings the story. You're barely moving now. Just a slow rise and fall of breath, your body sinking deeper into the sheets, while your mind drifts weightless in this ocean of light. It's time to meet the photon, the mysterious little traveler that carries light across the universe. Now you might think a photon is just a tiny marble of light buzzing through space like a laser pointer on a sugar rush. But photons don't play by normal rules. They're weird, like quantum-level weird. A photon has no mass. It can't sit still. It always moves at exactly the speed of light, or not at all. You never find a photon taking a break, or just vibing. It's either go or nowhere. It also doesn't exist in one place until you force it to. It's not just a particle. It's also a wave, a probability, a shimmering maybe in the cosmic equation. Until you observe it. Then pop, it behaves like a particle. But turn your back and it's all wave again. Like it's changing shape just to mess with you. Imagine a friend who's solid when you look at them, but misty fog when you're not. That's a photon. This is what quantum physicists mean when they say light is a wave-particle duality. It's not that it flips back and forth, it's that it is both all the time, and our human brains just aren't equipped to hold both images at once. So we go with the one that feels less like a headache. And yet, despite its mood swings, The photon is the backbone of your entire visual world. It's how you know someone smiled at you, how you read texts, how you watched that one YouTube video where a raccoon stole cat food in slow motion. Photons are everywhere. They're born in stars bounced off your lamp, scattered in the atmosphere to make blue skies. And despite being massless, they carry momentum. A photon can push things. You could, in theory, sail on light. And that's not just sci-fi babble. We've actually built solar sails, giant, ultra-thin sheets that get pushed by the pressure of sunlight. One's floating out there right now, coasting slowly, silently, beyond the grip of Earth, carried by nothing but starlight. So light has force, even when it weighs nothing. And the rules it follows. They're some of the most precise we've ever discovered. Quantum electrodynamics. Our theory of how light and matter interact is accurate to something like 1 part in a billion. That's like predicting the distance from Earth to the moon to within the width of a human hair. And yet, scientists still debate the true nature of the photon. Is it a vibrating quantum field? A blip in an underlying reality, just a convenient fiction we invented to make math work? No one really knows. But we do know what it can do. It can dance, it can bounce, it can tunnel through walls. Oh yes, photons can pull off a stunt called quantum tunneling, where they disappear from one side of a barrier and reappear on the other, like a magician cheating at cards. This isn't just theoretical, it happens in real electronics. It's part of how your phone's chip works. You're literally holding a box of controlled photon sorcery. Meanwhile, here's something entirely unrelated and wonderful. Tardigrades can survive in space. These microscopic, water-loving creatures, also known as water bears, can endure the vacuum of space cosmic radiation and temperatures near absolute zero. They just curl up into a dehydrated ball and wait it out. You, on the other hand, need snacks, blankets, and podcasts to survive a cold night. Anyway, back to our shimmering friends. One more brain twist for the road. Photons don't experience time. From their perspective, the moment they're created and the moment they're absorbed are the same. There's no travel, no aging, no passage. A photon from the Big Bang is just now hitting your retina. And for that photon, it happened instantly. No waiting, no journey, just beaming through eternity like a cosmic shortcut. And now that it's hit you, it becomes part of your memory, of your imagination, of the strange, half-awake moment you're floating in right now. So here's the quiet miracle. You are constantly being touched by ancient light. Messages from stars, signals from atoms, leftovers from creation. And every photon that lands in your eye is a tiny, massless whisper saying, "I made it." You blink in the dark, and a photon dies. But its journey continues in you. And that somehow feels like both science and poetry. Your body is still, but your mind is lit like a cozy observatory under starry skies, quietly flipping through pages of light and time. By now, you've made peace with light's weirdness, its duality, its drama, its strict refusal to be outrun. But just when you think you've settled into the limits, science pokes you with another oddball question. What about faster-than-light particles? Not the regular stuff, the electrons and photons and dinner leftovers made of atoms. No, we're talking tachyons. These are hypothetical particles dreamt up by theoretical physicists to explore what would happen if something always moved faster than light. Not just could move faster, but was born faster. From the very start. It sounds fun at first. Like, ooh, faster than light. Time traveler vibes. Let's break physics. But tachyons come with baggage. The moment you put one in your equations, reality starts sweating. Because they don't just move faster than light. They exist in a realm where time doesn't work properly. A tachyon could arrive at a destination before it left. It could, in theory, receive a message before it was written. Events unravel, timelines fold, and you can bet that makes scientists twitch. So far, no one's found a tachyon. Not in particle accelerators, not in deep space, not in weird basement labs where conspiracy YouTubers think the truth is hidden. Still, the math allows them. And that's the irritating thing about math. It doesn't care how weird something is. If it fits the rules, it might exist. So tachyons live in that curious gray area, mathematically possible, physically unconfirmed, philosophically terrifying, which is very on-brand for the universe. Now here's where things get really spicy. In some interpretations of quantum mechanics, faster-than-light effects do appear. Take quantum entanglement, for example. Two particles are created in a way that links them together. Measure one and the other's state is instantly determined, no matter how far apart they are. Light years, galaxies. The distance doesn't matter. Einstein called it spooky action at a distance, which is pretty casual language for something that seems to break the entire universe's speed rules. But, and this is important, no information is actually traveling faster than light. You can't use entanglement to send a message. You can't write, "Hi, Grandma, I love you" into a quantum state and beam it across the galaxy. It's just spooky, not useful, like a haunted house that never gives you snacks. So the speed limit holds. Even when the universe feels like it's cheating, it's not. It just likes to flex. Scientists still debate what entanglement really means. Some think it suggests a deeper layer of physics. Others say it's just quantum math doing its weird little dance. But none of them have found a way to make faster-than-light communication happen. Not yet. Not even close. Meanwhile, here's a palate cleanser. Slime molds can solve mazes. Yeah. These blob-like brainless organisms can find the shortest path through a complex maze to reach food. They don't think. They don't plan. They just ooze toward solutions. So next time you can't find your keys, just remember. A gooey puddle of biological pudding might be better at puzzles than you. Anyway, back to light speed limits. Why are scientists so obsessed with these faster-than-light loopholes, you wonder? Because if we could send information faster than light, we could rewrite causality. And if causality breaks, so does everything else. Physics isn't just about numbers. It's about story. Something happens. Then something else. If events lose their order, then you can't define motion, memory, or meaning. Suddenly cause doesn't lead to effect. Choices don't shape outcomes. You'd have a universe with no plot. Just chaotic data swirling like static. And the universe loves a good plot. You stretch a little under the blankets, realizing the irony. Light, the thing that moves fastest, is also the thing that slows everything else down. It's the cosmic referee, the thread that keeps the story in order, the rule that stops your future from showing up in yesterday's lunch. And maybe that's not just a scientific necessity. Maybe it's a kindness. After all, we humans aren't built to handle all at once. We need before and after, now and then. We need a beginning, a middle, and something we can call the end, even if it's just a chapter in a bedtime science story. So as your breath slows and the room fades to softness, you hold this in your head like a quiet little secret. Light could be chaos, but it chooses to be order. It could rush, but instead it dances. You drift further now, as if your body is curling into the folds of time itself. The world is dim and still, but your thoughts, they've gone quantum. So far, we've danced with photons, dodged tachyons, brushed against Einstein in his pajamas, but now we're stepping into truly strange territory. Stranger than imaginary mass. Stranger than space bending like soft rubber. Stranger than blue glowing particle pools. We're talking about quantum entanglement again. But this time, with feeling. You remember it, two particles become linked. Measure one and the other immediately knows. Doesn't matter if it's in your coffee mug or chilling near Alpha Centauri. Their states are tied together, twin coins flipping across the cosmos. You can't control what result you get when you measure one of them. But once you do, the other one falls into place perfectly coordinated, instantaneously. It sounds like faster than light communication, but it's not. And that drives people bananas, because it feels like a message is moving, but it's not information. It's not usable. You can't rig the system to cheat causality. You can't send secrets or win arguments across galaxies. Still, scientists aren't done arguing about it. Some say entanglement hints at deeper connections in space-time, maybe even a hidden network like the universe has quantum Wi-Fi. Others insist it's all perfectly ordinary, if your idea of ordinary includes particles existing in multiple states until you force them to pick a side. It's a debate as fierce as it is sleep-deprived, because entanglement sits at the weird intersection of light-time and what counts as real. If you can't send information with it, but it still behaves as if something happened instantly, does that mean something did? Or are we just misunderstanding time again because time at the quantum level gets fuzzy? Events don't tick forward like a metronome. They blur. They unoccur. They exist in a haze of could be until something or someone watches. You pull your blanket higher. This is starting to feel less like science and more like cosmic poetry. But here's the strange, comforting twist. Even in all this fuzziness, light's speed still holds. It's a rule that quantum weirdness hasn't broken. Not yet. Not even with its wildest card tricks. And it's a good thing. Because if quantum entanglement really could send messages instantly, you could build a supercomputer that solves problems before you ask them. You could break every encryption system. You could spy without moving. You could ruin the internet. So far, though, nature's been responsible. She lets the particles dance, but never lets them speak. You know what else doesn't speak? Jellyfish. But some species can glow, change shape, and survive for immense periods of time without brains or hearts. Turritopsis dohrnii, for example, can technically live forever. It reverts its cells to a younger state when stressed, essentially starting over. A creature that defies aging, doesn't use light, doesn't care about physics, just vibes. Anyway, let's circle back to information. The universe has a deep, almost sacred obsession with it. Not just moving it, but protecting it. There's even a principle in physics called information conservation, which says that once information exists about a particle's position, state, or interaction, it can't be destroyed. Not truly. Not even inside a black hole. Stephen Hawking once thought that black holes do destroy information. But that led to a crisis, because if information can be destroyed, so can predictability, determinism, physics itself. So now many physicists believe that the information doesn't vanish. It's just scrambled like an interstellar egg smeared on the event horizon. And the thing that carries all that cosmic gossip: light. Photons are the messengers, the reporters, the town criers of the universe. They don't just travel, they tell. Which is why we look up at stars and say, that one's 12 billion years old. Because its light informed us. It didn't move faster than it should. It just moved exactly fast enough to preserve the story. You feel it now. That rhythm. The click of a photon born in fusion. The glide across a void. The whisper onto your skin. The sensation of being told, you are here and I have arrived. It's slow by cosmic standards, but it's beautiful. like a letter delivered by hand, not emailed, not pinged, not zipped across servers, just traveled with care. So when you lie here, half asleep, half entangled in thought, remember the universe has rules, even in its strangest corners. And light is the rule that all other rules respect. Not because it's fast, but because it's fair. Somewhere far beyond your room, beyond your neighborhood, even beyond the swirl of your galaxy light is still racing. It's passing ancient stars, slipping past dying planets, gliding silently through the vacuum with no eyes to see it, no hands to catch it. And yet, it keeps going. You stare at the ceiling, cozy in your blanket cocoon, and your thoughts take a sudden turn. Could we use light to travel through time, not just see the past through ancient starlight, but actually move through time? Forward, backward, sideways, if that's a thing. It's a favorite question among sci-fi fans, physicists, and insomniacs. And oddly enough, the answer is, sort of. But not how you think. You can't build a time machine out of a flashlight. You can't surf on a photon and pop out in the Jurassic. But light and the rules that bind it do help define the boundaries of time travel. Let's break it down gently. First, forward time travel is easy. In fact, you're doing it right now. Every second you're moving into the future just slowly and very predictably. But if you want to speed that up, all you need is relativity. Remember, the faster you go, the slower your clock ticks compared to someone else's. Zoom around at near light speed, and you'll age less than your twin who stayed on Earth. So yes, technically, astronauts are very tiny time travelers. And if you built a ship that could circle a black hole at the right speed, you could return to Earth thousands of years in the future while only aging a few hours yourself. That's forward time travel. No paradox, no fuss. Backward time travel, though. That's where things break down. Some theories suggest that under the right conditions, with wormholes, rotating universes, or space-time loops, you could create a closed, time-like curve. A path through space and time that eventually leads you back to where you started. Sounds wild, right? But the math works, sort of, under very extreme, very imaginary conditions. And every time someone figures out how it might work, another physicist steps in and says, "Yeah, but quantum mechanics hates that." Or, "Sorry, that would collapse into a black hole." Or, "No, because paradox. Because backward time travel invites contradictions. Could you prevent your own birth? Could you send yourself a message and then choose not to read it? Could you listen to this bedtime science story before I wrote it? Probably not. The universe, as it turns out, hates cheaters. And light, it's the enforcer. Because the speed of light doesn't just limit how fast things move, it limits how information flows. And without information flowing in the right order, reality stops making sense. Which is why no one's built a backwards time machine. Not yet. Scientists still debate whether time itself is an illusion. Some argue that the past, present, and future all exist equally, that time doesn't flow, we just experience it sequentially. Others think time is emergent, like temperature or color, something that comes from deeper physics we don't yet understand. But regardless of which theory wins, light is always there, moving from past to present, guiding causality like a cosmic shepherd, never faster than allowed, never out of place. And here's a beautiful detail: time stops at light speed. From a photon's perspective, the moment it's emitted and the moment it's absorbed are the same. No journey, no in-between, just an eternal now. So in a way, light is timeless, not in the poetic sense, in the mathematical physics textbook. This breaks your brain sense. And when you build your entire idea of time around things that aren't timeless, it starts to feel like time is more of a construct than a constant. A convenient framework, a hallway made of photons. Meanwhile, your brain reminds you, elephants can hear with their feet. Yeah. Low-frequency vibrations like distant thunder can travel through the ground and be detected by sensitive nerve endings in their toes. It's called seismic communication, which is a gentle reminder that senses like time are flexible. Light lets you see. But the earth hums and elephants listen. Back in your bed, you wiggle your toes slightly, maybe wondering what kind of signals are passing underneath you. Subways, storms, the quiet pulse of geological time you don't know, but light knows. It touches everything. And even though it can't go back, can't cheat, can't loop, it still brings you the past, gently, faithfully, always right on time. Because while time travel might not be real, memory is. And light is the first storyteller. It paints your bedroom in dim reflections. It carries the faces of people you miss. It sculpts old photographs into frozen whispers. It never breaks the rules, but it lets you remember. And maybe that's enough. The room is silent now, like the hush before dawn. Outside, the world sleeps, but your mind is wide awake, floating gently in orbit around a single glowing truth. Light isn't just how you see, it's how you know. And tonight, you're starting to see light as more than just photons or particles or waveforms on a graph. Light is reality's boundary keeper. It defines what can reach you, what can affect you, what can even exist for you. And now it's time to talk about that boundary on a deeper level. Because the speed of light isn't just a limit on particles. It's written into the equations of the universe itself. Every law of physics, the ones about gravity, electricity, magnetism, motion, time, they all assume this speed limit. It's not just a side effect, it's the constant that keeps the math from collapsing like a cheap deck of cards. In fact, the speed of light is so fundamental it shows up in places you wouldn't expect. Like mass. You've heard it before, Einstein's most famous baby E equals mc2. It looks simple, but it means that mass is energy, and the speed of light is what ties them together. That isn't just a variable, it's the conversion rate. It tells you how much energy is packed into every bit of mass, which means, in a very real sense, the speed of light is what lets matter be matter. You squint into the dark processing that. Light speed connects energy to existence, and it's not the only place it shows up. Take Maxwell's equations, the 19th century crown jewels of electromagnetism. They describe how electric and magnetic fields interact. And if you solve them, something amazing falls out. A self-sustaining wave that moves through empty space at, exactly the speed of light. Which is how we discovered the speed of light in the first place. Not by watching photons, but by solving equations and realizing, wait a minute. These numbers suggest there's a wave that propagates at 299,792,458 meters per second. And that wave was light. So light isn't just some lucky particle racing through space. It's a feature of the universe. The same speed pops up in Einstein's theory of special relativity, which governs how time and space warp at high speeds. There too, the speed of light acts like a firewall. You can approach it, but you can't cross it. You can bend space. You can stretch time. But you never break cis. Scientists still debate whether this speed is truly universal. Could there be places or conditions where it shifts? Some cosmologists think the early universe may have had different physical constants. Others argue that C is baked into the very fabric of space-time, that changing it would unravel reality. Because if you did change the speed of light, everything else would have to change too. Gravity would behave differently. Atoms might fall apart. The stars would never form. Even the passage of time would feel wrong. You'd be living in a version of the universe where the laws don't hum in harmony. They screech. They stutter. And yet in this universe, your universe, they don't. Because C is constant, immovable, sacred. You roll onto your back and stare upward even though there's only ceiling above. But in your mind, the ceiling fades. It becomes a dome of stars, ancient and bright. And you remember, you're not just looking at stars. You're looking at what light allows you to know. Even the cosmic microwave background, the oldest light in the universe, is bound by this speed. It's still traveling, still cooling, still bringing whispers from a time when atoms had just begun to form. That light is everywhere. It's the backdrop of existence. It's why your microwave works. Seriously, it's tuned to the same wavelength. And it's all governed by that one weird number 299,792,458, which, if you're curious, is defined exactly, not measured, defined. In fact, the meter itself, yes, the meter, that standard unit of length, is based on the speed of light. We define a meter as the distance light travels in a vacuum in 1,299,792,458 of a second. So every ruler, every tape measure, every "this room is 4.5 meters wide" moment is a measurement of how far light goes in a sliver of time, which means your entire physical reality is being measured in photons. And somehow, that feels deeply right. Here's a weird side note before your brain fully melts. There are more molecules in a glass of water than stars in the universe. That's not a poetic exaggeration. It's math. A single glass contains roughly 10 to 25 molecules. There are only about 23 stars. So next time you drink water, remember you're holding a cosmos in your hand. Just like now you're holding the whole light-speed universe in your thoughts. You yawn. You're still not quite asleep. But something in your chest softens. Because this limit, this speed, this unbreakable law isn't a prison. It's a shape, a structure, a constant heartbeat in a universe of chaos. By now, your thoughts are wrapped in photons. Every breath feels softer. Every second more elastic. You're not just lying in bed anymore. You're cradled in light's architecture. You start to think bigger now, much bigger. Let's leave your room, your neighborhood, even your Earth behind. You're floating far above, outside the Milky Way, looking down at billions of stars arranged in spiral arms like a glowing pinwheel on velvet. And beyond that, more galaxies. Each with 100 billion stars, each star pouring out light, each beam of light obeying that one speed. But here's the thing, the universe itself is expanding, and not just casually accelerating, like the fabric of space is being stretched, not from within, but from between. And as space expands, something really weird happens. It outruns the light trying to cross it. Let that sink in. Space is expanding faster than the speed of light can travel across it. Not the stuff inside space, but the space itself. And since light can't keep up, entire galaxies are being pulled away from us so fast. Their light will never reach us. They are disappearing. Not because they've exploded or faded, but because the distance between us is stretching faster than their light can bridge it. You might wonder, isn't that breaking the speed of light? Nope, because the rule only says that nothing can move through space faster than light. But space itself, it can stretch however it wants. It's like standing on a rubber treadmill that's speeding up under your feet. And no matter how fast you run, the edge is always slipping farther away. This is the foundation of cosmic inflation, the idea that in the first micro moments of the universe, space expanded faster than light ever could. not particles, not matter. Space. And it still is. That's why the observable universe is just a slice, roughly 93 billion light-years wide, even though the universe itself might be infinite. Because we only see the parts where light has had enough time to reach us. Everything beyond that hidden, blocked, not by walls but by distance growing too fast. So when you stare at the night sky, you're not just seeing stars, you're seeing the shrinking circle of the knowable universe, a light bubble, a cosmic echo chamber, and it's shrinking. The stars you see now, many of them are already gone. Their light will fade and future generations will never know they existed, which is haunting and beautiful and a little bit romantic. Because right now you get to see them. You live in a thin golden window when galaxies are still visible, when the cosmic news is still arriving. Billions of years from now, there may be only blackness, no more starlight, no more whispers from the past. Scientists still debate how long we'll have access to these distant signals, how far we can stretch our telescopes before the silence wins, how long until we're alone with just our own galaxy like a lighthouse in the fog. And yet even then, light will still define what's real. It will still be the limit, the map, the storyteller. Speaking of which, your eyes can only see a tiny sliver of the electromagnetic spectrum. Between infrared and ultraviolet, just a narrow band called visible light. All the color, texture, and depth you've ever known. It fits in one small slice of what light can actually be. There's more out there. So much more. Microwaves, radio waves, X-rays, gamma rays. Each invisible to you, each as real as blue and green. The universe is humming in symphonies you'll never hear, buzzing with messages you'll never decode, flashing with lights you'll never see, unless you build machines to help you. And we have. Telescopes that see microwave echoes from the Big Bang, sensors that detect X-rays from collapsing stars, instruments that pick up the ghost of starlight stretched into radio waves by cosmic expansion. In every case, light is the medium. It's how we stretch our perception. It's how we remember the beginning. Even when space is moving faster than light, even when galaxies vanish behind a growing curtain of distance, even when the darkness seems complete, light still leaves a trace. And you're lucky enough to be alive when the sky is still full. So tonight, when you eventually close your eyes and fade to dreams, just remember you are one of the last few billion people who will ever see this exact light. You're not sure when it happened, maybe a few pages of thought ago, but the stars outside your window feel different now. Not just sparkles, not just decoration. They feel temporary. Fragile, like postcards from a distant friend who might never write again. And as that truth settles into your pillow-soft consciousness, your focus turns inward. Let's talk about you, your eyes, your brain, your beautifully limited machinery for sensing light. Because all this talk about photons and cosmic speed limits, none of it matters unless someone's receiving the message. And right now that someone is you. You don't just detect light, you interpret it. You give it shape, color, emotion. It starts with the eye. Inside millions of photoreceptor cells, rods and cones stand like sentries. Rods see in grayscale, perfect for low light. Cones, they handle color. Red, green, blue. Just those three. Yet your brain, like some over-caffeinated visual DJ, blends them into every shade you've ever seen. The golden hue of morning light. That's not in the light. It's in you. Because color isn't a property of objects. It's a reaction. a neural illusion triggered by certain wavelengths of electromagnetic radiation. That's right, what you call blue or pink or sunset orange is just your brain labeling frequency data. Different creatures see different spectrums. Bees can see ultraviolet. Snakes detect infrared. Mantis shrimp. They have 16 types of photoreceptors that's triple what we have. Their world is a riot of color we can't even imagine. Meanwhile, humans, we see about 0.5% of the total electromagnetic spectrum. A speck, a whisper, a cosmic keyhole. And yet through that narrow slit, we've painted masterpieces, built telescopes, studied galaxies, fallen in love under starlight we barely even perceive. That's the miracle. You don't need the whole spectrum. You just need enough to wonder. Scientists still debate how real color is. Some say it's entirely constructed, nothing but subjective categorization. Others argue that color perception helped us survive ripe fruit, red wounds, green leaves. But no one doubts its emotional power. That splash of gold at the edge of dusk. That sudden warmth of candlelight on a cold night. It's not just photons. It's meaning carried on a wave. Here's something fun, the blue you see in the sky. It's scattered sunlight. Tiny molecules in Earth's atmosphere scatter high-frequency blue light more than red. That's why the sky isn't violet, even though violet scatters more, because your eyes just aren't as sensitive to it. In short, you don't see the sky as it is. You see the sky as you're built to see it. And there's something comforting in that. Because maybe you don't need perfect data. Maybe you just need a story you can live inside. And light is that story. When it enters your eyes, it becomes perception. When it hits your skin, it becomes warmth. When it spills through your window at dawn, it becomes hope. You've been surrounded by light your entire life, bathed in it, shaped by it, defined by its boundaries and its gifts. It draws the edges of your reality. It tells you where you end and everything else begins. It gives texture to shadow and volume to form. And yet, for all its power, light is also incredibly delicate. One cloud, one blink, one closed door, and it's gone. But it always returns. Even now, as your room slips into darkness and your senses quiet, your brain is still glowing with remembered light. Shapes, colors, faces, sunrises, screens, smiles, photons have come and gone, but their messages linger. And your brain is a cathedral of light's leftovers, echoes bouncing around neurons, patterns of color stored as emotion, flickers of memory wrapped in warmth. Even dreams are made of light, you just project it from the inside. And so, maybe it's no surprise that we use light as a metaphor for truth. I see what you mean. It just dawned on me. You're a bright one. We equate light with understanding. Because the moment something becomes visible, it becomes real. And the speed of light. It isn't just how fast light travels. It's how fast reality becomes yours. You don't receive the universe instantly. You get it one light second at a time, gently, patiently, so you can absorb it, so you can shape it into meaning, so you can lie here now wrapped in the gravity of your own thoughts and know you are not in darkness. You are inside the slow unfolding of light. Your body feels weightless now, not from floating exactly, but from settling. Like you've finally found the pause between two heartbeats and decided to stay there. And in that quiet, a final realization floats to the surface. You've spent this entire night chasing a question, why does light have a speed limit? And you've followed it through equations and paradoxes, black holes and jellyfish. Einstein's imagination, and the edges of the observable universe. And now, here you are, staring at the ceiling. Or maybe not staring at all, just listening, feeling. And the answer is still strange, because the speed of light isn't some cosmic coincidence. It's not a number picked at random by a bored god with a stopwatch. It's foundational, a silent agreement between space and time, a contract written into the blueprint of everything. It defines how fast anything, matter, energy, information, even causality, can travel. If you tried to go faster, you'd break the timeline, undo cause and effect, rip the fabric of reality into narrative spaghetti. The speed of light isn't arbitrary, it's protective, like a seatbelt built into the cosmos, not to limit you, but to hold you together. And the beautiful thing is, everything respects it. Stars respect it. Electrons respect it. Black holes, gravitational waves, quantum fields, your own vision, they all bow to the same rule. Even the expansion of the universe, wild and accelerating as it is, doesn't break it. It just works around it like a clever loophole in the code. The result, a universe that feels coherent. Because that speed, 299,792, 458 meters per second, isn't just how light travels. It's the pulse of how reality unfolds. Scientists still debate whether it's the upper limit of all interaction, or whether there's some deeper layer of physics where the concept of speed doesn't even make sense anymore. Maybe something stranger is waiting beyond the veil, something timeless, spaceless, ruleless. But here in the world, you know light's limit is the rule that gives you before and after. That separates memories from imagination. That lets events stack in the right order so you can say, that happened. And then this. Without it, the world would be chaos. And here's the twist that slips into your mind like a lullaby. Maybe it's a good thing we can't outrun light. Because if we could, if everything happened all at once, if information and consequence collapsed into a blur, you'd never get a chance to process your life. You'd never get to feel time pass, or grow, or change, or forgive, or remember, or dream. Light's delay is what gives you space to be human. It's not a cosmic flaw. It's a design feature. It's why we fall in love gradually, why we learn through stories, why music unfolds one note at a time instead of all at once. It's why you're lying here now, gently drifting between thoughts, while the light outside your window races across space just fast enough to bring the stars to you, but slow enough for you to wonder what they mean. Here's one last curious thought. If light were instantaneous, the night sky would vanish. You'd only see stars as they are now, which means you'd see almost nothing. Just blankness. The beauty of the stars comes from the delay, from seeing light that's old, from watching the past arrive moment by glittering moment. And that somehow is what gives the universe its texture, its age, its depth. Without the speed of light, the cosmos would be flat. But with it, the cosmos is a story. And now, as your breath slows and your eyelids flutter in that final tug of war with sleep, you realize you never really needed the answer to that question. You just needed the journey, the slow, curious, beautiful journey, carried on beams of light. And now, we slow everything down. Let the thoughts loosen. Let the questions go unanswered for just a little while longer. You've traveled far tonight without moving at all. You followed photons across billions of years. You touched the edge of black holes peaked into tangled quantum knots and stood still while the universe expanded beneath your feet. And through it all, light was there. Moving, always moving, but never too fast. Never too fast to carry meaning. never too fast to outrun mystery. And that is the magic of it. Because if light had no limit, you wouldn't notice it. You wouldn't wonder about it. You wouldn't lie awake at night tracing it from your window to the stars and back again. Its slowness, relative as it may be, is what gives us time to feel, to listen, to change. It lets the universe unfold rather than collapse. It makes room for stories, room for music, room for dreams. You're a dreamer tonight, drifting through soft shadows and the final flickers of thought, not trying to solve anything anymore, just resting in the glow of the question. Maybe that's all we ever needed, not the answers, but the time to ask them, the space to hold them gently. And so, as the stars outside continue to whisper and the night carries you farther from waking, let yourself disappear into the hush. The light will keep traveling, the universe will keep unfolding, and your mind, beautiful, curious, weightless, can rest for a while. You don't need to catch the light tonight. Just let it pass through you, like a lullaby in motion, like a sigh at the edge of time. End of script. Good night.